Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
We are going through a course of lectures on crystal structure and their properties, and in this lecture the contents will be as follows: symmetry operations, importance of symmetry operations, piezoelectric effect, and a few problems. We have been seeing the various symmetry operations. Based on symmetry operations, we are able to show that pentagons cannot be placed side by side to fill up 2-dimensional space. Based on other symmetry operations, it is possible to show that all the solids that we think of or we come across should fall in one of the 14 lattices which have been named after Bravais. They are called the Bravais lattices. All these things we have seen, and once again we are seeing some more things related to symmetry operations, and again I am showing this for the simple reason how the symmetry operations are related to the physical properties. If you tell me what symmetry is possessed by a particular crystal, the property can be inferred, right. There is a connection between symmetry and physical property. This is a very beautiful concept. This is what is observed. Now, I am showing one of the symmetry operations, namely reflection. The human body has got mirror reflection. Suppose you cut me into 2 halves, then the right half is a mirror image of the left and vice versa. If you properly comb your head, then the mirror reflection body has got mirror reflection. The left half is the mirror image of the right half and so on. So, similarly, now the mirror reflection means for every point x there will be a point x prime. Better thing will be you look at your spectacles. This lens is a mirror reflection of this lens, right. This can be thought of as if you cut this in 2 half, or you place a mirror here, this can be obtained, right. The 1 half can be obtained, that is what. So, this is a mirror reflection of this one and vice versa. Similarly, if you have a hand, you have 2 hands, right. So, the right is a mirror reflection of the left, and similarly now you can cut this chair, right, as the human body, the left half the chair is a mirror reflection of the right half and vice versa. The other possible thing is a rotation. You have got 2 atoms here, you have got hydrogen here, you consider these 2 as oxygen atoms, then this is the H2O molecule, you have got H here, O here, as is shown here. Now, what is the kind of rotation which will take it back to the original system? What is a symmetry operation? A symmetry operation is an operation which leaves the system invariant. Now, you take this crystal structure, the body centered cubic structure. If I rotate this BCC structure through 90 degrees, right, it goes to the same configuration, right. The equivalent or identical configuration is obtained for every 90-degree rotation, it goes to identical configuration, right, rotation through 90 degrees, right, this cubic lattice. Similarly, the water molecule, you got two hydrogen atoms and the oxygen atom here. After you rotate through 180 degree, right, clockwise or anti-clockwise, then you go back to the same, the H will go here, this H will go here, right. So, that is called rotation, but not through 90 degrees, right, only 180 degree rotation will get you the system back. Then you go to what is called inversion center. Now, today's lecture will be mostly concentrated on the inversion center. What do you mean by inversion center? Look at this diagram. Now, you got x 2 here, there is a point here for the coordinates. So, supposing you take x 2, this will be this is x 2, you can have y 2 also here, right, this is along the x direction. Suppose this is the y direction, then the coordinates of this will be x 2 y 2, then corresponding to x 2 y 2 you have got x 5, that should be minus x 2 minus y 2. So, the animation shows upon inversion, that means this system has got inversion symmetry, because x 2 goes to x 5, right. This has got a inversion center. Whenever you perform an operation, they are called the point group operations. The operations are done, rotation is done or reflection is done about a point. This is a point, about this point, the point m is the point about which the operation is done. Now, what is the operation that is being done? Does it have inversion center? Now, it has an inversion center, because for the point x 2, you have got x 2 will come here, right. What I can do is I can make, does it have inversion center? Let me ask. Now, whether this has inversion center, you take this origin, the coordinates are 0 0 0. What are the coordinates of this atom? X y z. Do you have an atom at minus x minus y minus z? You have an atom here, you got atom here and you got atom here, and if this is origin with the coordinates 0 0 0, then you got atom here at the coordinates x y z, and if there is an atom for x minus x minus y minus z, if that condition is satisfied, then the system has got inversion center. Cube has got an inversion center. A non-cubic system will not have inversion center. I have told you much about the inversion center. For every point x y z, if there is an identical point at minus x minus y minus z, then the system is said to have inversion center. Now, this inversion center has got potential significance because of the property, namely piezoelectricity. Now, let me complete this inversion center. So, the m is the center of inversion is there around the point m. So, every point x 2, there is a point x 5, for every point x 1, there will be a point at x 4. Suppose the coordinates of this are x and y, there is an identical point here at minus x minus y. So, it has got an inversion center, right, that is what I told you just now. So, in a 2-dimensional space, you got x y, then x 4 corresponds to minus x minus y. Okay. This particular structure or this figure has got inversion center. Let us talk about piezoelectricity. Who discovered piezoelectricity? The credit goes to the Curie family, or in particular Pierre Curie discovered piezoelectricity. Now, what is piezoelectricity? You take a material, consider this as the material, right. You compress the material, you apply pressure, right. You compress the material, then what you observe is the upper side and the lower side, between these two faces a potential is developed, right. A voltage is developed, that is called the piezoelectric effect. So, piezoelectric effect simply means you take an object or you take a material, you apply stress on both faces, then across these two faces you get a potential or the voltage, right. Okay. And the important point is here, I will be talking about importance of planes, because of the fact there is what is called electromechanical coupling coefficient. I will come to that later. This implies or indicates the conversion efficiency, how much mechanical energy is converted into electrical energy or vice versa, right. I told you about the piezoelectric effect. When you apply pressure, there a voltage will be developed. You see, instead of being 0, the piezoelectric material, instead of the voltmeter showing a 0 reading, it shows a finite value when you apply stress across the two faces, right. This is the so called piezoelectric effect. From the application point of view, rather than the piezoelectric effect itself, the inverse piezoelectric effect is important. In applying a constant pressure and observing voltage, you do the other way around. You apply a alternating voltage, then what will happen to material? If you apply a alternating voltage, the voltage goes back and forth, then what will happen to crystal now? When you apply stress, means the size is reduced, you get a voltage. Then when you remove the pressure, the voltage will come back to 0. Now what I do is I apply a alternating voltage. When I apply alternating voltage, the crystal will begin to vibrate. These thickness vibrations are the so called ultrasonic waves, right, or a sonar. So now what you will observe is you get the ultrasonic waves are produced by a material like barium titanate. You have a crystal here, the crystal structure of barium titanate. You have got barium atoms at the corners, titanium atom sits at the center, and oxygen atoms are found at the corners of the 6 faces, right. Okay, you got the oxygen atoms here at the face centers, and at the corners you got barium, and the titanium is found at the center of the cube. So, barium titanate is a piezoelectric material, right, the piezoelectric material. Now the inverse piezoelectric effect is important, because when you apply an alternating voltage across the piezoelectric material, then the crystal will begin to vibrate. And you have heard of sonar. What is sonar? Sound navigation and ranging. Where do you make use of sonar? It is fitted to all submarines, okay, naval ships. They can detect the enemy submarine. The waves can travel through water or any liquid. So, the ultrasonic waves can travel through solids and liquids. So, you know, something like radar, you send a ultrasonic pulse, then if a foreign body is there, it will the wave will come back, otherwise it will not come back. Now, therefore, ultrasonic waves can be produced and can be effectively used to determine, to see whether enemy submarine is found in the sea. And not only that, very many flaws, defects in materials can be detected. Defects in material, what? In a nuclear reactor, in the automobiles and the blades, you know, the aircraft blades, all materials, the defects can be detected by ultrasonic waves. You know, the problems can be a defect or a broken thing can be observed by the human body, can be seen by X-rays. Similarly, the ultrasonic waves are very powerful to see the defects in the metallic materials, not only materials, in biological systems also. I mean the gallbladder stones, and not only the gallbladder stones, even the sex of the baby in the womb can be seen by the ultrasonic waves. Ultrasonic waves or the inverse piezoelectricity acquires quite considerable significance, because it has got immense applications. In every hospital you have got a sonogram, a sonography. You could have seen sonography, ultrasonic sonography in every hospital, because of the fact the gallbladder stones can be detected, and again very many other things, even the sex of the baby can be detected by ultrasonics. Now, I have been trying to explain to you the importance of planes, the crystalline planes, and the connection between the symmetry of the crystals and the properties What do you mean by crystalline plane? This is a crystalline plane, right? Any plane that contains the atoms in a crystalline, this is a plane, is a crystalline plane. Now, how will you distinguish between this plane and can you think of some other plane? You can think of a plane like this. It is passing through these two atoms and center and also the two atoms at the bottom, right. This plane will contain how many atoms? 1, 2, 3, 4 and 5. This plane will pass through 5 atoms, whereas this plane that you see here will pass through only 4 atoms. And so, this plane is different from the plane that passes through center of the cube. These two planes are different, right. Now, therefore, the number of atoms through which each plane will be passing will be different. So, the potential and many other properties will become different. We talk of again why planes are important. You talk of cleavage plane in crystals. You take NaCl crystal, when you cut it, it will be, it can be cut easily only along certain planes. They are called the cleavage planes. Single crystal of NaCl being cleaved with a razor blade, right. This is what is shown in here. Not only planes are important and directions are also important. You have heard of plane of polarization in light, in optics. So, plane of polarization or a plane of vibration. So, the plane is important in piezoelectricity, plane is important in NaCl, that is what is shown just now. The planes are important in optics. Similarly, directions are also important. I will not deal much with the directions, but what I would like to tell you is the directions are also important, right. If a light ray passes through a material like this, which shows what is called double refraction. All of you would have studied refraction, but not double refraction. Double refraction means for every incident ray there will be 2 refracted rays. For every image there will be 2 images, right. When you see the images through doubly refracting material, for every source is a point, right. You got a point here, then you will be having, you will be observing 2 points. Instead of a single point, you got a, you make a pencil mark, you got a dot, you see through doubly refracting material, then you will observe 2 points. That is what you are seeing here. One pencil, you know, it appears to be like 2, right. When you see the pencil through calcite crystal, right, when you see the, it is a doubly refracting material. So, only along certain directions the double refraction will be seen, right. Double refraction means for every incident beam there will be 2 refracted beams, right. That means for every object there will be 2 images, that will be seen only along certain directions. So, directions are also important. Similarly, when you talk of magnetization, now you see hard and easy directions of magnetization. You take a magnetic material, you know certain magnetic materials, when you apply a magnetic field they can be magnetized, but the amount of magnetization that is induced in the material will depend upon the direction. If you apply the magnetic field along 1 0 1 bar 0 direction for this crystal, right, you got a crystal here, this is the direction, this is the direction 1 0 1 bar 0, this is the direction. When if you apply a magnetic field along this direction, then the amount of magnetization that is produced for a applied field is only this much. But on the other hand, if you apply the magnetic field along 0 0 1 direction, this is the direction 0 0 1 direction, then the field acquired by the material is shown by the red curve. The value is much larger. For the same applied field, the magnetization is much larger along the 0 0 1 direction compared to 1 0 0 1 bar 0 direction. So, that is the reason why it is called easy direction of magnetization, whereas this is called a difficult direction of magnetization or the hard directions. And so, you would have studied easy and difficult directions of magnetizations. So, the amount of magnetism that could be induced in the material depends upon the direction or differs from direction to direction. So, the magnetocrystalline anisotropy of cobalt is shown here. Easy and difficult directions of magnetization are shown in this picture. Then I go to symmetry and physical properties in crystals. Once again, I will be again concentrating on the piezoelectric materials. There is an intimate relation between the physical properties of substances and the symmetry elements. Let us illustrate this for a piezoelectric crystals. In certain crystals, as I told you earlier, application of external mechanical stress or pressure develops or induces a net dipole moment, which produces electric polarization with the polarization charges appearing on the surfaces of the crystals. This phenomenon is known as piezoelectricity. As I told you just now, if you apply pressure, this becomes positively polarized and negative charges will be found at the bottom, and there will be a polarization density or there will be a field that can be developed across the two faces. The upper portion becomes positive compared to the lower portion. In the case of quartz crystal, the unit cell is electrically neutral, and the charge centroids of the positive and negative they coincide. In a certain crystals, as I have been telling you, the application of external mechanical stress induces a net dipole moment, which produces the electric polarization with the polarization charges appearing on the surface of the crystals. This phenomenon is known as piezoelectricity. In the case of a quartz crystal, the unit cell is neutral. When is it neutral? Now, you take the crystal here, this is a crystal, right, this is a piezoelectric crystal. Now, you see here ions, right. Supposing you consider the white circles as positive ions, the positive and negative charge centroids they coincide in the absence of a stress. You do not apply any stress. This is a whole crystal containing both the open circles and darkened circles. Let us assume the open circle as positive ions, the darker circles as negative ions. What do you find? You find here 3 open circles, right. Here it is a hexagonal kind of thing that you have got here, 3 open circles and 3 dark circles, right. So, there will be 3 positive ions, 1 here, 2 here, 3 here, and they are located in such a way that you have got a equilateral triangle, right. You have got a triangle wherein the positive charge center will be found here, right. At the centroid of the triangle, the positive charge will be accumulated, or the something like center of gravity. The positive charge center will be at the centroid. What about the negative charge center? That will be also at the centroid of the triangle. You take this triangle, the lower triangle, okay, you see another triangle here, right, which is connecting the negative ions. You see another triangle, right. Now, for this triangle, again the centroid is the same, right. For these 2 triangles, the centroid is the same, and it will look as if the positive and negative charge centers will be coinciding. So, the crystal as a whole will be neutral. That is what I am trying to tell you now. Apply any stress, right. The positive and negative charge centers, they coincide with each other as shown in the figure. Now, what happens to the crystal when you apply stress, right. Okay. When you apply stress, what happens to the crystal? Now, this atom has moved inwards, and similarly this atom with a positive charge also has moved inward. Thereby, the centroids have been disturbed now. The positive charge centroid and negative charge centroid, these two centroids were coinciding with each other in the earlier case. Now, let me ask you a question, a fundamental question, a very important question. Now, when you look at this hexagon, does it have inversion center? You tell me whether this has inversion center. You have an atom, this is the origin, right? You have got an ion here at x and y, this is a two dimensional thing, right? At x and y, they are the coordinates of the ion here. For what about the ion for the coordinates minus x minus y? If you have got a similar ion at minus x and minus y, then it has got inversion center, right. Now, do you observe a similar ion here? You have got an ion here. What about this ion? It is a negative ion. Now, what at if you call this the coordinates of this point as x and y, for minus x minus y, you are having this ion, right. The coordinates of this ion will be minus x minus y, and you have got an ion here. If you have got a similar ion here, right, what about this ion? It is a negative ion. If you would have got a negative ion here, a dark circle and a dark circle, then the system has got a inversion center. Now, let me again ask the question whether this system or whether this crystal has got inversion center. The answer is no, because you have got a negative ion. On the other hand, you have got a open circle, it is a positive ion here, right. For the coordinates x y, you got a negative ion. You have minus x minus y here, the center of this ion, you have got a different ion, not the same ion. If you would have had the same ion similar to this kind of thing, then the system would have had the inversion center. In this case, it lacks inversion center, it does not have inversion center. So, this crystal which I am talking about is non-centrosymmetric. Now, therefore, the center of symmetry in these crystals is absent. Let me now pass on to the summary session of my talk. The summary goes as follows. The symmetry operations have a bearing on the physical properties. By physical properties, what I mean is the electrical property or the mechanical property and the optical property, all the properties are intimately related to the symmetry. Okay. If a material were to be piezoelectric, it should be non-centrosymmetric. Why piezoelectric crystals are important? Because they are used in sonar fitted to ships to detect enemy submarines, and again very many biological applications which are possessed by the piezoelectric materials. We will pass on to the question session. The question number 1, what is mirror reflection? Question number 2, does the human body exhibit inversion symmetry? Name an effect which exhibits the relation between symmetry and physical property. With this, we come to the end of this lecture. The rest of the things with regard to piezoelectricity, I will continue in the next lecture. Thank you.